Continuing on with example 1, now part C wants what is the linear regression of the data? We're going to round to 3 decimal places. Now here's your instructions for creating a linear regression, but I want to emphasize that I can start right here because I have already entered in this data to make this scatter plot. If we did not make the scatter plot in our calculator, I would still need to go to stat, hit enter or for the edit, and enter my data into list 1 and list 2. Go to y equals, clear out the equation, and turn the plot 1 on. Okay, so I would still need to go through that step of importing all of that data into my calculator. So since we've already done that, we can pick up right here. So we will go to stat, and I'm going to arrow over here to calc. Because we have decided that a linear regression is the best fit, I'm going to go down here to number 4, or you can just punch in 4, whichever one you want. Now we have some options here, and I'm going to show you what this kind of does, but it's not really necessary to do it this time. So I'm just going to leave that out, and I'm just going to arrow down here to calculate. I'm going to skip all that optional stuff for right now. Okay, so we're going to go right here to calculate. And here is my linear regression. Okay, so we have a variable for A and for B, and we're rounding to 3 decimal places. So my A is 1.57. That second 6 makes that first 6 go up to a 7. So that is 1.577. And then my B is 1.892. That 4 makes that 2 stay. 1.892. Now it tells me what A and B equal, and it tells me what the equation is that it's using. So it is using the equation y equals ax plus b. So instead of y equals mx plus b, they're using a different variable for that m, but it's the exact same equation. So I have my equation and what my variables equal, so now just substitute everything in. We have y equals, my A is 1.577x plus my B of 1.892. So this is my linear regression. Now it wants to know, is this equation a good fit? Meaning a good fit of the data points. Well, we can tell one of 2 ways. The reason we turned that diagnostic on is so that we could get this r squared and this r. Now, sometimes we only see r squared and r doesn't pop up, but a lot of times we're going to get r squared and r. And that r is going to help me determine if the equation is a good fit. So it says the goodness of fit of a line to the set of data points can be observed from the graph of the line and the data points on the same set of axes, which I'm going to do after this. And it can be measured if your graphing utility computes a correlation coefficient, which is what these R's are representing. The correlation coefficient is a number R, and it can go anywhere from -1 to 1. And that measures the strength of the linear relationship that exists among the 2 variables. And then I've highlighted. The closer that your absolute value of R is to 1, the more closely the data points fit the linear regression. So here, because my A, or my R, and I'm going to say is about 0.9992. Okay, 0.9992. That second 2 makes that 2 stay. Because this is so close to 1, and even if this was negative 0.99992, okay, because it's the absolute value. So really, the closer it is to -1 or 1, the better this regression is. So because this is so close to 1, is this equation a good fit? Yes. That's why we need to turn that diagnostic on. Now, It also tells me that the goodness of fit from the data points, they can be observed from the graph of the line and the data points on the same axis. So what I can do here is I can go to my y equals, and I'm going to put in my equation of best fit. So 1.577x plus 1.892, and then hit enter. And you can see how good it hits those points. It looks like it hits 2 of them quite perfectly, and then all the other ones are really, really close to that. So yes, this is a great fit.